Well, this is John Black, super chemist. Time is a result of information carriers moving at a constant velocity of c. What is time? It's a noun. And a noun is a person, place, thing, or idea. Which one is time? Is it a person? No. Place? No. Thing? No. It's an abstract noun. That means that it is an idea or quality or state rather than a concrete object. So as you can see, it's not a concrete object. And what's abstract mean? It means it's existing in thought or as an idea, but not having a physical or concrete existence. It doesn't exist, except in your mind as an idea. That's what time is, a noun that's an abstract noun. So you can see it's not a thing that you can walk through or a dimension or anything like that. Instead of thinking of a photon clock where the photon thing goes back and forth, bouncing back, I want you to think of these. These are neurons, in your brain, basically nerve cells. And in between there's always a gap. They don't touch each other. So how do they communicate? They throw information carriers back and forth between the neurons. Now, if you're standing still, you can see it has, let's say it takes a second. Okay, you can say an hour, you can say a minute, whatever. Let's just arbitrarily pick a unit of time called the second. Let's say it takes 1 second go from here to here. If you're standing still, this would be a second. But let's say you're moving. Now this synapse here wants to send a information carrier to here, but it can't do that because you're moving this way. You're moving to the right. So the photon goes here. And you can see this is longer than the red, right? The vertical. Because you can see it's obviously a hypotenuse. So what does that mean when you move like this and you make the line longer? Okay, remember the information carriers move at a constant velocity of c. Instead of a photon or information carrier, I'm a guy that's driving and I have a car that goes 50 miles an hour and this is 50 miles. So every time you have to talk to one neuron to the other, I get in my car, I drive, it takes me an hour to get here. Well, what if you start moving? Now this distance has doubled and my car only goes 50 miles an hour. So what does that mean? That means information took twice as long to get from here to here. You have slowed down the flow of information. You haven't slowed down time because time isn't a thing, okay? It's an idea. You slowed down the flow of information that the information carriers can give from one synapse to the other synapse. Really, look down here. Let's say you're moving super, super duper fast, right? You can see the blue line. It's like 3 times as big as the red line now. The information carriers all move at constant velocity c. Then you have taken the time it takes to get from here to here. You've tripled it. What you need to understand is this new line is your second. This is a second. This is a second. They're all seconds. But when you're moving, you make the second stretch out. Let's say 4 times this line is than this line. That means it takes you 4 times as long to think to have any thoughts go through your mind. 4 times as long. Because the distance is 4 times longer for the information carrier to carry the information from one synapse to the other. See, this is what gamma is. Gamma is the hypotenuse over vertical line. The vertical is always 1. 1 second, 1 hour, whatever you picked, whatever unit of time. Gamma is just a ratio of your new second compared to the second that you would have had if you were standing still. So if the hypotenuse is twice as big, then you will have time take twice as long to happen. Right? Physics will take twice as long to happen. So it's just a ratio of those two, your second standing still and your second while you're moving, or hour or year, whatever you want to call whatever unit of time you're talking about. That's why it's always greater than or equal to 1, because the hypotenuse has always got to be bigger than this. If it's 1, then the hypotenuse isn't really a hypotenuse. It's just a vertical line straight up and down, and there's no difference between it and the red line. They're the same exact thing, so it's a 1. Just look at this. Doesn't this look exactly like a photon clock? Your synapses, they're just acting like a photon clock. Okay, so this is your hand on your clock. These are atoms in your hand on your clock. This is second 1, 2, 3. The motor will tell this hand to rotate. what will happen is first atom will throw a information carrier to the second atom, and then that atom will send a information carrier back to the first atom. Then the first atom moves. You can see it's moved a little bit here. Then the second atom does the same thing, sends an information carrier to this atom. This atom sends an information carrier back. Then it moves. This continues on until it goes up until all the atoms in the hand have rotated. Obviously this happens like almost instantaneously. You can't see this. Then when it gets to the last atom, right, it throws out an information carrier. It doesn't wait for an information carrier to come back because it just moves. Because the field, like the reason why these atoms waited was because the field, it could feel the field. The field up here that it combined with this one, it couldn't move without that information carrier coming back and telling them to move. Why do I say it's two-way communication? Because that fixes this problem. When you're going from left to right, you always have your photon clock. What about when it's here? You can see they don't mesh up. You got a little hand here and then a big jump here. These are even. This fixes that because this and this are equal. But you can see, even force carriers are information carriers. They move at a constant velocity of c. So these, the information to tell each atom to move or rotate, right, in this hand, is now, because you're moving, you make the length in between longer. So it takes longer for the information carrier to give the information to rotate or move, accelerate, you know. And you can see, again, you're making a right triangle. The blue line is the hypotenuse, so it's always bigger. By moving, you always make this line longer. And when you slow down, it gets smaller and smaller and smaller. But once you stand still, that's the smallest it can be. It can't be any smaller because you can't. If you're standing still, that means you're moving the slowest you can move. You can't move any slower than this. So that's why I call it the Planck length, even though it's not. The Planck second or Planck length is really the smallest distance to take a picture of. This isn't really that. It's not really the Planck length, but it is the smallest unit of time that you could have. Meaning it's the smallest second you can have, or if you want to call this an hour, then it's the smallest hour then you can have. You can call it a year, then it's the smallest year that you can have. And again, gamma tells you, this over this, hypotenuse over vertical line, gives you gamma. If this line is twice as long, then you have been time dilated two times. That means everything takes twice as long to get information. This isn't just for synapses. It's not just for mechanical clocks or mechanical acceleration. It's not just for photon clocks. It's for all physics relies on this. You might say, well, it takes me 2 seconds here. I start moving, and now my 1 second takes me 2 seconds. First of all, your new second doesn't take 2 seconds. It takes 1 second. But relative to a standing still second, it is 2 times as long. Okay? And only then, though. It's an actual new second. It's not that your heartbeat takes 2 seconds now to beat. No, that 2 seconds is your new second. That's an actual second now in your frame. The reason why you don't have a heart attack is because, your heart takes 2 seconds now to beat, right? But your new second is that 2 seconds. And all of your biomechanisms, right, to tell you, hey, you're having a heart attack, they have been delayed the same amount of time, okay? So if your heart takes 2 seconds now to beat, well, so what? It's supposed to take that long, okay, according to all your biomechanisms. And you've created this new second instead of this second. But I hope you do realize that all you're doing is you're making this line shorter or longer, and that determines your length of time, or your length of a second. Your thinking, your electronics, everything in physics relies on information carriers, and they all move at a constant velocity of c. So if you start moving, you make the line longer. You make it so it takes longer to get information. It takes longer for physics to work. Physics runs at this rate. If you make it this long, then it goes fast. If you make it here, it's going to slow down because it takes longer for the information to get from one atom to the other. So let's go over this, and then we'll get more in depth about this. Okay. So how does this happen? It's because you're moving. The faster you move, the slower your clock moves, because you got more distance in between the atoms on your clock, more distance in between your synapses. Everything slows down. So it's all due to velocity. Okay, and we're going to get into, that's why I'm saying we'll get back to this, because it's all about acceleration. But there's two types of acceleration. There's speed, changing your speed, and changing your direction. But let's move on. This is for like a spaceship. If you're, if you're moving fast or you're accelerating up, you make your speed different. But what about, let's say you're rotating. Okay, you're rotating on this thing. Boom, boom, boom. Think about a photon clock, or there's two synapses. You have one synapse up here, and you have another synapse down here. If you're rotating, the thing is going to want to, if you have a drop a ball right here, it's going to go this way. It's going to go off on a tangent. Same way with your photons. If you throw a photon out of synapse here and you want to throw it here, but you're rotating, your photon's going to go off at a tangent. And when you hit here, this will be here. They're going to hit this spot at the same time. So basically, you have the same exact thing. Your horizontal, your vertical is still your, smallest unit of time. If you were standing still, your photon will go back and forth in your synapses like this, and you'd only have this little bit of distance that you have to go. But now you start rotating. You start rotating. You start rotating. Now you have a longer distance. You have this line. You have this dotted line here. You would have had your photon would have gone this far, but now it has to move this far because you are rotating. Just like up here, your photon should have went this far if you were standing still, but you started moving, making it go longer and longer. Take a long time. So it dilated, time dilated. And then what goes on with the Earth, right? We're going to come back to these. We're just going to do a fast thing here. Look at here. Here's your geodesics. This is the North wants to go here. The South wants to go here, right? And I split them up so you can see they're equal angles here. You're just doing the inverse here. This is the red line. This is your vertical. This is where you want, if you were standing still and you weren't on this planet, your photon would just go like this. But you ain't doing that, are you? Because on planets, there's something called gravity, okay? So instead of your photon going like this, your photon is now going like this. So I hope you see that, time, why I say it's a result of something. The information carriers, they are forced to move at 186,000 miles per second relative to space-time. And because of that, time progresses on. You can't turn back time because you'd have to go to every photon in the whole universe and force them to go back in the opposite direction. Okay, you can't do that. All right, it's not a place, it's just a result. Okay, or consequence that happens because these information carriers are forced to move at sea. That's why time progresses, because it can't be stopped, because you can't change this fact that information carriers move at sea. So that creates time, and you're moving through space faster creates time dilation. Okay, you're not moving in another dimension called time. You are just moving through space faster, and you're stretching out the distance that it takes information carriers to do physics. So you've slowed down physics. So time is an idea, meaning a mathematical construct that represents mathematically the consequences or results of information carriers forced to move at sea relative to space-time. Time represents the rate or speed that physics can actually happen at. And time dilation is a consequence of moving through space, faster, and changing the rate that physics can happen at. Whether it's done by a rocket, a spinny thing, rotation, or a planet's gravity. You make the information carriers travel longer by moving. So obviously if they have to move at the same, speed, obviously then the flow rate of information that is needed for physics will slow down.